So far, what we have done is we have learned how to apply the method of weighted residuals to arbitrary equations. I have also given you an assignment which needs to be submitted, where you will write a small MATLAB program to solve a simple differential equation. And you will use the finite element method to do that. We have talked about one-dimensional problems. We have also talked about two-dimensional problems. But in reality, we have not actually completed talking about two-dimensional problems. And that is what I'm going to do today. And to do that, I am going to take now the Poisson's equation and apply the method of weighted residual to Poisson's equation. So what I'm going to do is I'm going to use the Poisson's equation and I'm going to apply the method of weighted residual to Poisson's equation. And in the process, we will finish off whatever we have still not considered about two-dimensional elements. Okay, so this is your Poisson's equation. Divergence of epsilon grad phi. So what I have done is I have not written it as del square phi, but it is similar. I have taken epsilon within the divergence. It is the same thing. So your equation has now been modified as divergence of epsilon grad phi plus rho is equal to 0. And when I compute, so if I'm going to apply the method of weighted residuals, the first thing that I need to do is I need to obtain the residual. So this is your residual. As I said, phi hat is your approximate solution, because you do understand that if you use a numerical technique, you're not going to be able to find the exact solution. So the exact solution is phi, and phi hat is your trial solution. So when you put the exact solution, you get 0 on the right-hand side, but when you put the trial solution, then you get a non-zero value on the right-hand side, and that, let us call that R, which is the residual. We would imagine that this value will be quite small. Now, if you want to apply the method of weighted residual, you need to weight it. So you take integration over the entire solution domain. Let's call that omega. It's a volume. WR d omega equal to 0. So over the entire solution, over the entire solution region, you take an integration of the weighted residual and set that to 0. So that is the whole point of using the method of weighted residual. Now, in the finite element method, this integration will have to be done element-wise, which means that you will have different solutions over every element, and you will separately obtain the integration over each element. So therefore, let us confine for the moment the problem space to one single element, and let us imagine that the part of the solution, so phi hat is the entire solution over the solution region, and that part of the solution which is confined over that particular element, let me call that phi hat E. So this is something like this. We're trying to find a total solution would probably be the collection of these yellow segments, but right now I'm concentrating only on one of these yellow segments. So I am calling that phi hat E, E being the element over which the solution is being considered. And we will go over every element at a time. So if I now write the residual for this particular element only, this is the equation, this is the expression that I have for the residual, but this is the residual over a particular element E, which is given by divergence of epsilon E grad phi hat E plus rho E equal to 0. Now, as I have told you, I will I will stress this further at the moment. When you are dealing with the finite elements methods, the number of elements or how you mesh your solution region is completely in your hands. And therefore, one thing that you're going to do is you are going to maintain the epsilon, the material permittivity, and the charge density uniform over every element. if you have an element where the charge density or the material permittivity changes, what you need to do is you need to break it up into two elements. Because remember, even though we are dealing with similarly sized elements, that's not necessary. You can take any size elements over the entire region. So the basic assumption is that permittivity and charge density is not going to change over a particular element. Okay, so now what will I do? We know that in this particular weighted residual method, we use the shape function as our weighting function. So I can replace W with S, and when I'm performing the integration over a particular element E, I need only to bother about that part of the shape function which is constrained, which lies over element E. So for example, when you take SI being the shape function at node I. Node I may be common to more than one element, and therefore it will have a non-zero value over more than one element. Fair enough, but we are not going to be bothered with that at the moment. When we are considering element number 1, we are going to only concern ourselves with element number 1 as element number E, and therefore we are going to perform this integration over element number E. So we only need to consider the value of the shape function over element E. So therefore now I write the revised form of the integration. The integration is now constrained over the domain of that particular element. So if it is a two-dimensional element, we are talking about a two-dimensional region. If it is a one-dimensional element, we are talking about integration over one dimension. So according to which dimension you're working on, your omega E will change, and therefore it will either be a single integral or a double integral or a triple integral. At the moment, I'm going to concern myself with two-dimensional problem. So I will assume that this omega E is a two-dimensional plane. So SIERE d omega E equal to 0. This is my modified integration. The integration takes place over the domain of the element E. I consider the weight function, the shape function, which is constrained for every node I, which is constrained only over the element E, the residual, the part of the residual which is defined over the element E. So I am completely concentrated on element E. Now, if I do that, I put the value of the residual, and this is what I get. Now, if you look at this portion, the second term, there's no problem. This will give you this term, integration omega E, rho E SIE equal to 0. These are your shape functions. Rho is considered to be constant over a particular element. So you just have to integrate the shape functions over an element, and you know how to do that. You actually know what the integration will come out to be. But let us look at the first term. The first term is divergence of a vector, because grad phi is a vector. Epsilon could be a tensor, but for the moment we are not going to consider, we are just going to consider isotropic material. So let us imagine that epsilon is also a constant. So what I am left with is SI, which is a scalar quantity, SI divergence dot grad phi, epsilon grad phi. Now you have this vector identity. If you have two vectors A and B, then A divergence of B is given by divergence of AB minus B grad A. So B grad A you already have. So therefore, this B grad A will be equal to first term minus second term, and that is what I apply here. So the first term reduces to SI epsilon taken out, grad phi dot dA. dA, because I have a two-dimensional problem. So I'm going to take the integration over the element. Okay. There is one step jump here. Wait a minute. What I will have is I will first have a volume integral over elements omega E of SI epsilon grad phi dot grad AA. And then I will have this term integration epsilon grad phi dot grad SI. So this term is there. And if you look at this term, I mean, the first term that you have here, which I have not written down, it is a volume integral over A. And this reduces to a surface integral, just as we did in the first case. So what we are doing here is we are reducing the volume integral into a surface integral. If you reduce the volume integral to a surface integral, and if you're working in 2 dimensions, then the surface integral reduces to a contour integral and the volume integral reduces to a double integral. So what you have is you now have 3 terms, out of which the last 2 terms are area integrals over the elements, and the first term reduces to a contour integral around the boundary of the elements. Is this point clear to everybody? I have skipped a step here. What you get is by applying this identity, you get first 2 double volume integrals. Out of this, I retain the second volume integral, and the first volume integral is reduced to a surface integral by applying Stokes function. So when I do that, I get this term, which in 2 dimension reduces to a line integral, and the volume integrals reduce to a area integral over the element. So the last 2 terms are area integrals. I am also going to, for the moment, assume that for whatever strange reason, the first term goes to 0. If you do that, then your equation reduces to the last 2 terms. So this is what you are left with. Integration over omega e. So here is the area integral over the region of the elements, or a 2-dimensional element and area element, epsilon e grad phi dot grad si d omega e minus rho e se equal to 0. So this is the integration that you need to perform over the element. Is this clear to everybody? Ashok?
Yes, ma'am.
Yes, ma'am, it's clear.
Nishant?
Yes, ma'am.
Okay, fine. So now what we have is we have an equation like this, just as we had in the previous case. Look at this, you have this equation in terms of the SIs. Now in a triangular element, you would have 3 eyes. So there are 3 nodes. So you will have 3 shape functions at this on these 3 nodes. So this is actually a 3 simultaneous equations which need to be solved. So the potential at the nodes of the triangle must satisfy the above equation. We would have 3 simultaneous equations for I equal to 1, 2, 3 at the 3 nodes. So what did we do? We took one element and we applied weighted residual. Using the triangular element, we applied weighted residual to Poisson's equation over this one particular element. And as a result, we ended up with 3 algebraic equations which need to be solved simultaneously. So then what does this mean? Now you will have to do this for every element that you have. Wait a minute. Yeah. Now suppose you have NE number of elements. So you will have to perform this integration for every element. So this will have to go from over E. You will, and you remember when we assemble, what happens is the contributions from every equation, if you have multiple contributions at a particular node, the contributions will add up for every element. So therefore, remember, the shape function at any node over a particular element will be 0 on all elements except those which are adjacent to node I. So if you have node I and node 1 is shared between element 1, 2, 3, you will have contributions to all matrices involving node 1 from elements 1, 2, 3, but you will have no contribution from the other elements. So therefore, what you now need to do is this equation, which gives you 3 simultaneous equations, when you assemble them over every element in your solution regime, what you will have is you will have to perform, this is your discretization rule, that the summation of these integrals, the 2 terms, there should be actually a brackets here. The summation is over the both these 2 terms. And the summation is taken over all E, but you really do not need to take the solution summation over every E. You take only the elements which are adjacent to node I. So therefore, your problem formulation now reduces to this function, summation E adjacent to I, where you take summation over the two integrals, summation over omega E, epsilon E grad phi dot SI d omega E minus rho E SI E equal to 0. So this entire summation has to go to 0. So you see, we are not trying to make the residual over every element go to 0, but rather we would like a situation where the average over all the elements of the residual goes to 0. This is called the weak formulation because we are using an equation which has a second order derivative, but we are only needing to compute the first derivative of phi, and therefore it has been reduced to a first order equation. Now here I have given you a fictitious mesh. This is easy to understand because, you know, I've broken it up into rectangles and then drawn the diagonals. So I have 15 nodes, 1 to 15 nodes, and I have 16 elements. This is my mesh, and I am going to apply this over this mesh. Now I want you to look at something interesting. Okay, first let us do that. So therefore I need to take summation over. So as I said, this is a two-dimensional problem. So every volume integral reduces to a double integral over x and y. So what you have is grad phi E dot grad SI dx dy. And the second term you have rho E, which is a constant SIE dx dy. So essentially you need to take the area integral of the shape function in the second term. And for the first term, you will have to take integration of the gradient of the shape function. So you're actually dealing with the shape functions. And remember, since you have expressed phi as SI phi, if you remember, then phi I are the constant values at the nodes, the nodal variables. So SI, the shape functions, hold the shape functions are dependent on xy, and whatever shape you have, the function has over xy will be determined by the shape function. So it is the shape functions which are dependent on xy. Now, if you remember, we have already obtained this from phi being equal to summation Si phi I. We have obtained the shape functions to be 1 by dp I plus qi x plus ri y. I've given you the values of PQR, or I've asked you to find the values of PQR in terms of ABC. And you know what the ABC coefficients are for Poisson's equation. So this is your equation. And if you evaluate the integral, this is something that you can do by yourselves at home. This is what you will end up with. Now, this is convenient because remember, PQR are coefficients which are only dependent upon the coordinates. So if you know xi, yi, you will be able to obtain pi, qi, ri for every node, and you get a stiffness matrix which is dependent on PQR only. And you have phi 1, phi 2, phi 3 as your nodal variables. This is, of course, for a local one element. You have to repeat this for every element to get the global stiffness matrix. So this is your, you can take epsilon out, you can take rho out, because for a particular element, epsilon and rho are constants. You keep getting this. PQR value will change from every element. Phi 1, phi 2, phi 3, you will get phi 4, phi 5, phi 6, and so on and so forth. So this is your local stiffness matrix. This is your local nodes vector. And this is your local force vector. Right? And then you need to assemble them together to get Kg, phi g, Fg. And as before, you need to find phi g in terms of K inverse F. Before you can do that, you have to impose the boundary conditions. Boundary conditions are whatever you have for your Poisson's equations. You can have this as, for example, your boundary conditions could be V equal to some known, phi equal to some known value on the top plates and equal to some, maybe the bottom plate is grounded. So for every, like 11, 12, 13, 14, 15 would be bounded nodes with phi equal to 0, and 1, 2, 3, 4, 5 will be bounded nodes with, let's say, phi equal to 100. You will also probably need some boundary conditions on the lateral sides. Do you need that? Firstly, have you understood what I have discussed so far? Any questions? Which is confusing? Which part should I discuss? Pratasha?
Ma'am, in the previous slide, you said that we will consider that, in previous to that slide, like, yeah, we'll consider the first term going to 0 by some means.
We'll come to that later. Apart from that.
Apart from that, I understood. And I think there will be lateral boundary conditions also because we have nodes in the lateral
Yes,
boundary.
you have nodes, and additionally, you must remember that Laplace's Poisson's equation is an elliptic equation, so it has to. It is a bounded value problem. So every boundary needs to be specified. Darshan?
Yes, ma'am, I understood.
You understood. So let me come to this question. What would be the boundary conditions on the lateral sides? Let's say this is an ideal parallel plate capacitor. I mean, of course, your boundary conditions depends upon the problem that you are solving. So since this is Poisson's equation that we are solving, let us take the simplest case that we always consider, the ideal parallel plate capacitor. So as I said, the top plate has a particular potential on it. The bottom plate is grounded. What would happen on the lateral boundaries?
Ma'am, we solved a problem like this on the second class maybe. So for the lateral boundaries, for the left side lateral boundary, we considered that it will be 0. The potential will be 0 for x is equal to.
That was a particular problem that I gave you, right? Now
Yes,
I'm giving you a physical problem where you need to figure out for yourself what the boundary conditions should be. So if this is a capacitor, what would be, so this is the dielectric inside the capacitor. So you will have on the top plate, it will have the potential of the metal plate on top of it. Similar for the grounded plate. What happens at the boundaries? What do you know about the boundaries in an ideal parallel plate capacitor? Do not neglect the words ideal. So the dielectric ends, let's say, in an ideal parallel plate capacitor, what would you have? You would have infinite plates.
Yes.
And what is the consequence of having considering infinite plates?
Ma'am, a uniform field will be there.
Uniform field, yes. And apart from that?
And there will not be any fringing in ideal.
There will be no fringing. There will be no fringing. If there is no fringing, if you imagine this is your dielectric, this is the boundary of your dielectric, and then let's say there's air beyond it. And if there is no fringing, what do you know about the field or the potential along this line joining node number 5 and node number 15? Do you have any information already?
Field line will be a straight line.
Field line will be straight line, meaning it will be parallel to the boundary.
Yes, ma'am.
The field line will be parallel to the boundary, which means what? There will be no normal component. The field line or the potential will,
linearly, potential will linearly vary from high plate.
That's okay. No, that's not the point. That is something we are trying to figure out. We know that will happen, but that is something we are trying to solve in this particular case. In fact, if you have rho, it may not vary linearly. So don't go there. The only thing that I have mentioned is, so you should not make assumptions. So the only thing that I have specified is that it's an ideal parallel plate capacitor, which means, as you have said, there is no fringing. And if there is no fringing, that means the field line is perpendicular, parallel to the boundary, which means that the field line will have no component which is perpendicular to the boundary. If you had a field line, which is like, if you had fringing, let us say, this is what it would look like, the field line, which means it would have a component which is normal to the boundary and which is tangential to the boundary, right? On the other hand, What you're saying is, no, your fill line is not going to be like this. Your fill line is going to be completely parallel to the boundary, which means this particular component is missing. So the normal component of the fill line, normal to the boundary, must be 0. Is this a valid boundary condition to assume on the sites?
Yes,
For an
ma'am.
ideal parallel plate capacitor.
Yes, ma'am.
Okay. So now I have identified the various boundary conditions. So I know what are the boundary conditions on the top. I know what are the boundary conditions on the left. And as Pratyasha said, what happens to this first equation? First term. The second two terms, where am I? The second two terms, of course, gives me the the stiffness matrix and the force vector. But a priori, I assume this first term goes to 0 and it's a contour integral. So what happens to this contour integral? Can I really take it to 0? And is it 0 only in specific cases, or is it always 0? That is the question. For that, what I'm going to do is, I'm going to consider a particular case. Let us imagine I have a 2-dimensional space, and let us say I have taken a snapshot of the mesh where it looks like this. That's acceptable. It's of course a special mesh because it's a hexagon. This is node AO, node 0, okay, node O, and A, B, C, D, etc. I have 6 elements, 1, 2, 3, 4, 5, 6. And let us imagine that over this 2-dimensional region, I am trying to evaluate this weighted residual of the Poisson's equation. Now, what will happen? What will the contribution be from the last 2 terms that we have already seen? So we don't need to bother about that. But we have not evaluated the first term, the surface integral. So what we will do is, for this particular case, we are going to evaluate the surface integrals and see what happens. So this is the surface integral that you need to evaluate. Let us consider element number 1, and let us consider node number 1. So here, what I need to do is, I need to perform the integration over contour 1, the contour of element 1, and the integration that I need to perform is S1. So I'm only considering, let's say this A is node number 1. I'm considering S1 over element 1, epsilon over element 1, phi hat over element 1, integrated over the area of element 1. Remember, when you're dealing with a 2-dimensional problem, an area integral reduces to a contour integral, and this dA reduces to a line integral. So basically what you need to do is, if this is your element number 1, you need to perform this integration over line AO, OC, and CA. So that's what I'm doing. I'm breaking it up into 3 parts. So integration over AO, integration over OC, integration over CA. What do I need to integrate? This term, S1, epsilon over element 1, tilde hat over element 1, grad tilde hat over element 1. And if I want to integrate along AO, I need to take the dot product of this quantity with the normal to this line AO, which is dot NAO, normal AO. Similarly, for OC, I have dot NOC, and for CA, I have the outward normal NCA, right? So I have 3 terms, and I have 3 normals, outward AO, outward OC, outward AC. Now, I also know that since the node A, or node number 1, is common to element 1 as well as 2, I will have contribution from element number 2. Right now, what I do is, I know that the first term gives me these 3 terms, and I leave them not evaluated. I leave them as it is. And then I go on to the second element. And I know in the second element, SI will be defined at node number A, and I will have to take the contour integral along the boundary of node number 2. Which means I will have to take the integration over OA, AB, and BO. So I will have, let's say when I'm taking over OA, I will again have S1, I will have epsilon over 2. Remember, my condition is that the permittivity cannot change within an element, but it can change from element to element. So epsilon over 1 need not be the same as epsilon over 2. And if you remember, when I asked you to write the program, when I asked you to write the input data file for a finite element program, I told you that for every element, you need to specify the element type. And the second thing that you need to specify is the material type. So if the material is different, you will need to specify the different permittivity for that material, for that element. Never mind, S1 epsilon 2 grad phi hat 2. So phi hat 2 can be completely different from phi hat 1. We are looking at different solutions of phi hat over the different elements, but S1 remains the same. And here I integrate this. Before I integrate this, I need to take the dot product over the outward normal, which will be normal to OA. So this will be in this direction. Again, AB will be in this direction and BO will be in this direction. Now, if you look at now, ultimately, what will you be doing? You will be taking, after you find these terms, remember what you need to do. You need to sum over all elements which are adjacent to I. Here I have shown you the summation over L, only term 2 and 3, because we had assumed that the term 1 is 0. But if term 1 is not 0, but instead it gives you 3 of these integrals, you have to take the summation of these 3 integrals also over every element. So that is what you need to do. You will have to, therefore, as you go along, you will need to take integration of every element. Now, element number A, as far as we can see, is common only to element 1 and element 2. It is not common to element 3, 4, 5, 6. For the moment, let us assume that this is your entire solution region. So therefore, it is only to be, you only need to add this contribution from element 1 and element 2. So let's do that. Let's add these 3 terms and these 3 terms together. When you add these 3 terms together, you see something. You have S1 epsilon 2 grad tilde hat 2 dot NOA, and then you have AB, you have BO, you have again, let me remove this. You have again AB, you have AO, OCCA, and you have OA, AB, BO. Now, the boundary that is common to these 2 elements is OA. So you actually have 2 integrations over AOA. And if you look at this integration is over AO of S1 epsilon grad phi. Now let us for a moment imagine that there is no change in permittivity across element 1 and element 2. So you have same epsilon over element 1 is equal to epsilon over element 2. And then you have phi hat 1 and you have phi hat 2. These are of course different. And then you have NA0 and you have NOA. Now, so S1 and S1 equal the integrands. If you look at the integrands, S1 is the same. Epsilon is the same. Would S1 be the same? Cannot S1 be different over the 2 different elements? Because when you consider S1 over element 1, you're considering one particular side of S1 and you're considering another part over element 2. So why do I say that S1 is the same? Can I really consider that S1 is same over element 1 and element 2 for this contour integral? I would like to say, see, I have written it as S1. I have not written it as S11. I have written, I mean, it doesn't matter. S11 and S12, I'm saying are equal for the purpose of evaluating OA and AO. And I'm also saying that grad phi tilde 1 is equal to grad phi tilde 2 for the purpose of evaluating this integral. So essentially, this, whatever you have here, S1 epsilon grad phi, is equal in this integral and this integral. But what is different is the normal. In one case, the normal is in the AO direction. In the other case, the normal is in the OA direction. So if over the same edge, you are evaluating an integration of a common quantity, once with the dot product in the outward direction and once with the dot product in the inward direction, these two must be equal and opposite. And as a result, when you add these 3 and 3 6 terms together, the contribution from OA from 1 and 2 will cancel out, and you will be left with the other 2 terms, the integration over AC and OC and integration over AO and BO. But the integration over AO will cancel out when you add the 2 elements, contributions from the 2 elements. Why is this so? Why can I do this? Who will answer? Should I repeat my question?
Ma'am, this OA is using the same S1 in both the cases.
Be a little more specific. You're probably right, but what is saying?
The shape function S1 is the same for element 1 and 2.
Why do you say that? Would not the shape function over element 1 depend upon the shape of element 1?
Ma'am, it will depend, but that side which it is sharing with the element 2.
Over the edge, it has to be the same.
Yes, ma'am.
Along OA, it can have different shapes. So if you remember that prism, the prism does not need to be symmetric, but along the edge OA, it will have the same value. It has to be unique. And what about phi hat? Phi hat 1 and phi hat 2. Phi hat 1 and phi hat 2 are definitely different functions. Let me go on to, for this, let me go on to the one-dimensional case. Oh, I'm sorry. What happened? Okay. Let me go on to the one-dimensional case. Look at this, huh? Or maybe we can look at the previous slide. Yeah. Now think about this. We are talking about an edge here. In a two-dimensional problem, you talk about a point because you share only a node between, a point between 2 elements. Now, if you look at the shape function, the shape function must be unique valued at node 1. Now, if these shape functions are not necessarily equal, you can have a situation where the weight functions don't necessarily look the same, right? So for example, H2 over element 1 and H2 over element 2 did not look the same. They're not symmetric, but at this node, it must be equal because it is one shape function, and we are taking that part of the shape function which is defined over node 1. It has a unique value. So similarly, if we extend this understanding to two-dimensional problem, you can imagine that along the edge OA, shape function S1 has a unique value, and then it can have a different shape over element 1 and a different shape over element 2. Agreed, everyone?
Yes, ma'am.
Okay.
Yes, ma'am.
What about phi hat and phi hat 2? Phi hat 1 and phi hat 2. Again, if you go back to the problem, as you can see,
Ma'am, as the nodal values was same, so here also the value at the line will be same for both, means at that line, at that edge.
okay, you are right what you're saying. Let me frame the question once more for everybody. We are looking at different values of phi 1, phi 2, phi 3. And phi 1, phi 2 are different functions. So for example, this yellow line is a completely different function from the second yellow line. So phi 1, phi 2 are different functions. Phi 1 and phi 1, 2 are different functions. So how am I saying that over these two integrals, where am I? Yeah, phi 1, phi tilde 1 and phi tilde 2, I'm assuming them to be equal because of inter-element continuity. These are piecewise linear continuous, and we have to assume that along the discontinuities between two edges, between two elements, you have a unique value. So therefore, the functions have only this constraint. Within the element, they can look different, but at the boundaries, you have to have a unique value. The functions have to be continuous, and therefore, only along the edge OA, this grad phi hat 2 and grad phi hat 1 must be equal. Nowhere else, only at this boundary OA, they are equal. So therefore, you can imagine that this integral over AO and this integral over OA are equal and opposite. And so when I add these three terms with these three terms, I end up with 4 terms, and these first 2 terms cancel each other out. Now remember, you're going to do this for every element. So by the time you have come round, you have contributions from every element over the common boundary. So any contribution that comes from OA, OB, these lines are not there, OC, OD, OE. So each of these boundaries between two elements will have equal and opposite contributions from every element, and they will ultimately cancel out. So when you ultimately take the sum over all the 6 elements, you will have, from these 2 elements, you will only have contributions of the integration over AB and the integration over AC. And then for 6, you will have integration over this segment, this segment, this segment, this segment. So basically what I'm saying is that when you evaluate this contour integral, where is the contour integral? When you evaluate this particular contour integral, I say take it to be 0. Don't take it to be 0. When you evaluate this contour integral over every inter-element boundary, and when you assemble all the contributions that come from the internal boundaries will cancel out, and you will be left with only contributions from the outer boundaries. So the entire solution regime is divided into any number of elements, and there will be a lot of internal boundaries between elements, and there will be some external boundaries which are not shared between elements, but which are boundaries to the solution geometry. Every contribution to this first term, which is a contour integral over an internal boundary, will cancel out. And when you have assembled the entire matrix, you will not have a 0 value for the first term, but the first term will give you a contribution over only the external boundaries of the system. Is this point clear to everybody?
Yes, ma'am.
You will have, so you can't really take this to 0, but you will have contribution only over the boundary of your solution regime. Now, what do I have? What do I know about the boundary of my solution regime? Let me go back to the previous slides. No, where I have the meshing. Yes. So that means when I perform this integration, all the contributions from this internal boundaries, 3, 9, 4, 10, 2, 4, 7, 8, all these will cancel out. You will only be left with the boundaries that are between 1 and 2, 2 and 3, 3 and 4, 4 and 5, 5, 10, 10, 15, and so on and so forth. So you will have only the boundaries between which are external to the external boundaries of the system. So these boundaries, these boundaries, these boundaries, and these boundaries. These are the boundaries over which you will need to evaluate your first integral. But then I have set it to 0. How justified am I? Can I, under any situation, set it to 0? Think about the boundary conditions that you have. Okay, let me go ahead and show you.
Ma'am, you told that the normal components at the outer sides are 0. So that's why we can sum them to 0, means equate them to 0.
All right. Yes. But what about the top and the bottom? And don't forget, it's not phi, it's grad phi, that is 0. Now, let me formally, you are already aware of this, let me formally define what kind of boundary conditions you have at a boundary. There are two kinds of boundary conditions which are possible, the Dirichlet boundary conditions and the Neumann boundary conditions. Dirichlet boundary conditions means that the solution variable is known at the boundary. The function has a known value at the boundary. That means in this particular case, phi I is given. That's true. For example, if you look at this problem, over the top plate, on the top of the dielectric, this boundary, you have Dirichlet boundary conditions because you actually know the value of the potential at every node. Node number 1, 2, 3, 4, 5, you know the potential. Potential is equal to 100, right? This is called the Dirichlet boundary condition. Similarly, at node number 11, 12, 13, 14, 15, you have the Dirichlet boundary condition phi equal to 0. So the solution variable that you're solving for phi is specified at a boundary, and that is considered to be the Dirichlet boundary condition. The second kind of boundary condition that you have is the Neumann boundary condition. And in this Neumann boundary condition, it is not the potential or not the value of the solution variable that is given, but the differential of the solution variable is given. So del phi, del n is given. So the normal component of phi is given. So del phi, del n is a given value. If del phi, del n is a given value at a boundary, then you say that at that boundary, the Neumann boundary condition is given. Now, let us imagine that this is given to be 0. For example, for a, For example, for a parallel plate capacitor, we have just discussed that along this boundary, there is no fringing, which means En is equal to 0. If you consider En is equal to 0, I have said that En is equal to 0, which means E is what? Grad phi. So this can be written as del phi by del n equal to 0. That is, the gradient of the potential in the normal direction is 0. That is what is specified. And this is the Neumann boundary condition. Similarly for this boundary. So first, what you have to figure out is what are the boundary conditions that are specified across the boundaries. On the top plate and the bottom plate, you have the boundary condition that you have Dirichlet boundary condition where phi is specified. And on the sides, you have the Neumann boundary condition, which is the normal component of the derivative of the solution variable is given. That is, del phi del n is given, which means that the normal component of E in the normal direction, that is the component of E in the normal direction, is given to be 0. It does not always have to be given to be 0, but in this particular case where we have assumed that there is no fringing, we can assume that it is 0. So we have Neumann boundary condition equal to 0, we have Neumann boundary condition equal to 0, and we have Dirichlet boundary condition. Now what happens in terms of the finite elements? If specified to 0, as Hitesh pointed out, this function will go to 0 because you have grad phi here. And therefore, you will have this integration will be evaluated as 0. So obviously, if you have Neumann boundary condition equal to 0, the first term gives you a 0 value. What happens when you have a Dirichlet boundary condition? So that means along the lateral edges, my assumption of the first term being equal to 0 is correct. But what about the top and bottom plates? What happens to this integral on the top and bottom plates? Top and bottom plates have Dirichlet boundary condition. What is the consequence of that in terms of solution? See, from these integrals, evaluating these integrals, you will obtain a stiffness matrix. Now, if, for example, in obtaining the stiffness matrix, I said that let this first term go to 0. And when you look at this particular problem that we are discussing, you can see that if you have Neumann boundary conditions, so first you have seen that you need not evaluate this first term over any of the elements which are internal. You only need to evaluate this term over the external boundaries. Moreover, if the external boundary has a Neumann boundary condition equal to 0, the integration comes out to be 0. So it's okay. But what about when you have a Dirichlet boundary condition? So for example, when you're looking at this problem, 1, 2, 3, 4, 5, you will have some contour integral, which will not have a 0 value over 1, 2, 2, 3, 3, 4. It will have some finite value. But ultimately, after obtaining this integral and obtaining every other integral, what will you do? You're not going to evaluate phi 1, phi 2, phi 3. You already know phi 1, phi 2, phi 3. You are going to impose the boundary conditions in your stiffness matrix in such a way that no matter what K1 gives you, what K2 gives you, your phi 1 comes out to be 100, phi 2 comes out to be 100, phi 3 comes out to be 100. Essentially, after you evaluate all these terms, K1, 1, etc., after you have the global stiffness matrix and the global force factor, in fact, you have the global equation matrix, what you will do is you will remove these terms. You will remove phi 1, phi 2, phi 3. You're not going to solve for phi 1, phi 2, phi 3. You are going to actually solve for only the internal terms. So whatever you have here has no meaning, is not going to influence the equation pertaining to phi 1 is irrelevant. The equation pertaining to phi 2 is irrelevant. So essentially, you are going to solve for a reduced system of linear equations, simultaneous linear equations, where phi 1, phi 2, phi 3 are not equations that you solve. So therefore, where you have the Dirichlet boundary condition, you need not evaluate these terms because anyway, they're not going to make any difference. Is this point clear to everybody? So I had told you that you do not need to evaluate the first term at all, which is a contour integral, which has to be evaluated over the boundary of every element. Then I showed you that you do not need to evaluate this over the internal boundaries because they will cancel each other out. Then I said that if you have Neumann boundary condition equal to 0, the integration comes out to be 0, so don't bother. Now I am saying that when you have a boundary which has Dirichlet boundary condition, even then don't evaluate, you don't need to bother because those terms, the equations for those nodes are anyway going to be removed from your system of equations. You don't actually throw out phi 1, phi 2, phi 3, phi 4, but you throw out the equations and replace them with equations such that phi 1, phi 2 comes out to be the given value. So you don't need to bother with the evaluation of the contour integral in any of these cases. Is this clear?
Yes, ma'am.
Ma'am, the force vector will contain the information about the potentials.
Potential?
I mean, just in 1D we did that. The first term used to contain 100, and the
oh, you mean the
last term used to
specified
contain
boundary
0.
condition? Yes, yes, yes. So you see, what you will do is after you evaluate all the stiffness matrices, you'll put them together, and once you put them together, when you assemble the matrix, after that you're going to impose the boundary conditions, which is a separate matter. I've taught you how to do the boundary conditions. But we know that the consequence of imposing the boundary conditions is that the stiffness matrix part does not matter. The force vector also does not matter. The force vector will have contribution from this term, right? Rho e into SI. This will go to the right-hand side. And that's okay. I mean, the value of the contour integral will give you some value, which will not matter because it can give you any value, but you're not going to use it for the solution. You're ultimately going to replace it with a specified boundary condition, a specified value of the boundary. So it does not matter. If you are convinced about this, then I'm going to go on to the next thing, which is one of the cases that we have missed. We have considered Dirichlet boundary condition. Dirichlet boundary conditions do not matter because if at a node a Dirichlet boundary condition is given, we don't care what the value of K phi comes out to be because it's not going to, we are not going to use that equation. However, that equation gets modified for the Dirichlet boundary conditions, we don't care because we are going to impose the boundary condition and it is not going to affect our solution. So we don't care. But there is one case that we have not considered. When del phi del n is equal to 0, the equation comes out to be, the integral comes out to be 0. But if your del phi del n is a given value, what happens then? This will be 0 only if phi hat is 0. Grad phi hat is 0. Phi is not 0. Grad phi hat is 0. So at a boundary, if grad phi hat is given to be 0, which means you're considering that the field is parallel. I'll give you the simplest case. If instead of considering ideal parallel plate capacitor, you consider a real parallel plate capacitor. In this case here, you will have fringing. So in that case, you will not have the condition that del phi del n equal to 0. Del phi del n will be equal to a positive flux outside the surface. So for example, if you have this situation, if this is your flux, let's say this is on the boundary between 5 to 15, the flux line is not parallel, it is curved, which means it will have a component del phi del n, which is not equal to 0, which will have a finite value, right? And if it has a finite value, the integral will not vanish. Do you get my point? What should I do then? What should I do then? It will not be 0. It will have a finite value. Any guesses what I should do?
Ma'am, it might happen that means the, like, suppose these are the sides of the dielectric. So whatever positive normal is there, that is going to be cancelled. No, ma'am, it won't cancel. It is positive.
No, but either del phi del n is 0 or it is given to you as a value. You have to need to know the normal component. Unless you know the normal component, unless you have the boundary condition, you cannot solve. You cannot obtain a unique solution. So del phi del n may be 0 or may not be 0, but it has to be given. So let's say it is given to a certain constant, let's say k. In which case you will be able to evaluate this integral. You will not be able to make it 0, but you can evaluate this integral. And where do you think this integral will go? Will it go into the stiffness matrix or the force vector?
Force vector.
Force vector. It will have no contribution from phi 1, phi 2. It will be like a input condition. It will be like rho. Because rho is known, you have a force vector on the right-hand side. Similarly, if you have a specified flux, so del phi del n is flux, right? If you know the flux out of a boundary, that is the Neumann boundary condition that is given at a boundary, and therefore you will be able to evaluate this integral. It will have a non-zero contribution. So at that point, you cannot ignore that first term. You will need to evaluate the first term. It will give you a non-zero value, which will go into the force vector and contribute to the force vector. So therefore, you know how to deal with every kind of boundary condition. You know how to deal with Dirichlet boundary condition. You also know how to deal with Neumann boundary condition, either if it is 0 or if it is non-zero. So for example, let us imagine that this is what is given. For simplicity, I have considered a boundary which is parallel to the x-axis. It is not necessary. So del phi del n is given to be q bar, let's say, that's the flux. So when I evaluate this, I take q bar out and I evaluate grad phi and I come up with a quantity like this. And this will of course go to the force vector, add to the force vector. It will not influence your stiffness matrix. Now, if for example, if it is not parallel to the x-axis, you have something, you will have an x component, you will have a y component. So del phi del n will be del phi del x nx plus del phi del y ny, and you will be able to evaluate this in a similar manner. So the point is that If you have a two-dimensional problem, you now know how to apply the method of weighted residual to this problem. You also know how to deal with the boundary conditions in terms of Dirichlet and Neumann boundary conditions. You also know how to evaluate the one contour integral term that you get and where it will contribute and how it will contribute. So the next assignment that you will have is to write a finite element program in 2-dimension for Poisson's equation. You have already been given an assignment, and that was a one-dimensional arbitrary equation. You will, after that, in the next assignment, you're going to modify that same, you can rewrite it. You are going to write it for Poisson's equation in 2 dimensions. And I would suggest, which I have already mentioned in the assignment, try to maintain the structure of the program that I have taught you. In the next class tomorrow, I will discuss once more the program of the program structure when you use finite element to kind of do a recapitulation so that you can easily write the program.